Hello, today we are going to be working on lesson topic 1.11, which is equivalent representations of polynomial and rational functions. And remember from previous lessons when we reviewed rational functions that you learned in Algebra 2, we reviewed that a rational function is made up of two polynomials, a polynomial on the top and a polynomial on the bottom. And that when the bottom is equal to 0, that's when the rational function becomes undefined. And that's when you're going to see a vertical asymptote occur. And it's going to occur at whatever that x value is where it is undefined. So we're going to work through some examples today and kind of look at some of these properties again, make sure everybody knows how to find them, do a little graph sketching, and then we're going to go back and talk more about those slant asymptotes that we kind of learned about a little bit in our lessons 1.7 and 1.8. So the first thing that we have here in this example is a rational function named h of x, and we are going to write an equation for h of x in factored form and find any values of x where there is a hole and where there is a vertical asymptote. So remember, a hole occurs at a factor that's canceled, so we're moving that point of discontinuity. And then a vertical asymptote occurs after everything has been factored, canceled, and removed from the equation, where there's still an x value in the denominator. So first thing we're going to do is write the equation in factored form. So we're going to factor the top of our rational function, which is just a difference of squares. So that is going to be x plus 2, x minus 2, and then we're going to factor the bottom of our polynomial. So the factors of 10 that add up to be 7 are 5 and 2. So that is going to be at x plus 2 and x plus 5. So that's step one, is factoring. So now we're going to look at what are the points of discontinuity that we can remove. Can we take out? What are those common factors? So they're going to happen here at x minus 2 and x minus 2. So that's where the hole is going to occur. After we remove the hole, notice that we have a different x left in the bottom. It's not x plus 2 left in the bottom, but x plus 5. So we're going to have a vertical asymptote on where that x value is at that factor. So if I have a hole at a common factor, so that means I'm going to take x plus 2 equal to 0, and I'm going to find that x is going to equal negative 2. So at this point, there is a hole at x equals negative 2. But that is the x value of the hole. If we wanted to find the location of the hole, then we would finish our problem out right here, and we would say the simplified version is x plus excuse me, is x plus 2 over x plus 5. And then we can plug this negative 2 back into this simplified expression, because at this point, this discontinuity, this hole, has been removed. So now there is no hole in the simplified version. And so we could locate the actual coordinate of the hole by finding the y value when we plug negative 2 into the expression. But we're going to stop right now at just where is it happening at, what x value is it occurring at. Then we're going to look at the vertical asymptote. So that's going to happen right here in the factor that's left after we canceled. That's unique. It's not the same thing as the whole. So then we would say x plus 5 equals 0. So then x is going to equal negative 5. And so then we would say we have a vertical asymptote at x equals negative 5. Okay, so once we have that and we know what can't work in our rational function, then we should be able to state the domain, which is actually what does work. So in other words, when we're trying to write our domain, we're not going to include the holes or the vertical asymptote. So our whole value is right here at x is negative 2. Our vertical asymptote is happening here at negative 5. So that means we can't include the negative 2 or the negative 5. So we have to exclude them. So when we exclude them, that means we're going to have a union symbol in our interval notation that would represent that. So I'm going to start out here, and it's going to, the first negative that I see, think about your number line, would be happening at negative 5. So that is going to go from negative infinity to negative 5. Then we're going to skip over that negative 5 because we can't include the vertical asymptote. And then we're going to go to where the whole is, which is at negative 2. Then we're going to skip over the negative 2, and then we're going to go out to positive infinity because all of the other x values will work for the domain. So there is my domain excluding the wholes and the vertical asymptotes. Okay, so let's start out by the next one, going ahead and getting the factored form. So we're going to get the factored form and write it on blank A. So pause your video for just a second, factor that thing for me, and then we'll move on. Okay, so hopefully you got this thing factored and you remember to take out the GCF of x because all of these have a factor of x in common. So I can pull that out first, which means then I'm going to be factoring the x squared plus the x minus the 20. I have two common factors, so I'm going to take that out, and we know that that's going to be the whole. We know that the x's left in the bottom that are unique to the problem that were not part of the whole right here, or the cancellation, would be a vertical asymptote at x and a vertical asymptote at x plus 5. So now the next thing we're going to do is to find the zeros of the function. So hopefully you remembered from previous studies that if the part that's canceled is the whole and the stuff that's left on the bottom is a vertical asymptote, where would you find the zeros? And so the zeros are going to happen after you've factored and canceled. Where are there x's left in the numerator? So all the pieces that are left have something to do with something significant on a rational function. So if we're trying to find the zeros of the function, I'm looking at the top, and so I would set x plus 3 equal to 0. So that is going to be when x equals negative 3. And now I realize you can do this in your head, and that's okay, but these are our notes. So if we're looking back at our notes, they should give us those little hints as to how we got to where we got. So this is finding the zero. Okay, so the next thing we're going to do is find the whole. And the wholes occur at where factors cancel that are unique. In other words, remember how in our lesson on 1.7 and 1.8, we talked about finding the zeros and the undefined values, but our function was a simplified rational function. So when we're identifying the simplified rational function, that's where we're going to get our information about vertical asymptotes and wholes. And we don't want to confuse the two, right? If this is factoring out and then we're left with an x minus 4 on bottom, it's a vertical asymptote because we're not going to have a whole on a vertical asymptote. So we always want to look at that final result. All right, so we are going to find any values of x where it has a whole. So that means in this particular problem, when it says values of x, we're just going to be writing our answer as x equals. We're not going to necessarily be finding the location of the whole. So I come up here to my problem, and I can see that this is the unique place that canceled. So I'm going to say x minus 4 equals 0, and that means the value of x at the whole is x equals 4. Now, I could find the location of the whole if I were asked to do so, and if I'm asked to do so, then the 4 that I got right here is going to be my x value, and then I'm going to put a 4 in here, here, and here, and calculate. So I'd have 4 plus 3 gives me 7 on top. I would have 4 plus 5 gives me 9, and then 9 times the 4 would give me this location right here. So this is what it would look like. Once we did that calculation, we get 1 over 36. But remember to read the instruction carefully, because here is not asking for the location of the whole. It's merely asking what's the x value of the whole. So if it's just the x value of whole, our answer is going to look like this. If it asks for you to locate the whole, then it's going to look like this. So we're just kind of making sure you're reading carefully and paying attention to what the question is asking. Then on D, we're going to find the vertical asymptotes of my function k of x, which is what we have up here. The vertical asymptotes are going to happen in the bottom where the x's are 0 once we have done our factoring and canceling and removing those discontinuity, or the points of discontinuity. Okay, so it looks like we have 2 x's left in bottom. So we're going to have 1 when x plus 5 equals 0, or at x equals negative 5, and then the other one is going to occur right here at the x, so that's going to be at x equals 0. So that's getting our vertical asymptotes. Remember, our horizontal asymptotes are referring to those special cases that we studied in 1.7 and 1.8. So our special cases have to do with the highest degree on top. So if I go back to my original problem right here, my highest degree on top of k of x is x squared, and my highest degree on bottom is x cubed. And so what did we learn about the case where the bottom dominates the top? That it's approaching 0. So it's going to have a horizontal asymptote at y equals 0. And then we're going to find the domain of the character or of the graph. And so to find the domain, then we're looking at how would we graph this. So before we talk about the domain, we're just going to kind of go through a rough sketch of what we know and put it on this graph over here. So we know we have a vertical asymptote at -5, so 1, 2, 3, 4, 5. And we know we have one at 0. We know we have a horizontal asymptote at 0. We know we have a hole at 4, 1, 2, 3, 4, and we already calculated it's 136, so it's kind of going to be down there somewhere. Just a little bit of a guesstimation on my part. Then we're going to have a 0 when x equals -3, so 1, 2, 3. And what else do we know? Well, I think that's probably it, that we should be able to get a fairly good graph. So we know that the graph is trapped between vertical asymptotes because, as we talked about in our previous lessons, the reason for those vertical asymptotes is the denominator of the rational function is trying to approach 0, and it just literally breaks the graph because you cannot divide by 0. So then you might want to plug in a few values. So I'm going to make me just a list of points here because I just need a few points to really rough sketch things in. So first off, if let's say let's focus between the two vertical asymptotes. So if I pick the number, let's see, this is 1, 2, or even let's just pick 1 because that would be easy to calculate. If I picked 1, then +1 here, then I could plug it back into the simplified version to get a point that I can graph. If I pick, so this is -1, and if I pick, what was this at? 1, 2, 3, if I pick, let's say 4, -4, then I could plug it back in and define my values. So I'm just going to make a list of x, y coordinates so to help me finish out this graph. So I'm going to find when x is -4, what's y? When x is -1, what's y? And then I need something over here on this side, so I'm going to pick -6. I already have a point to anchor over here. I can use the hole. So when I calculate -4, I put a -4 in here, and then I have a -4 here and a -4 here, and that's going to give me the value 1/4. And then I put a -1 in here, a -1 in here, a -1 in here. That's going to give me the value -1/2. And then I'm going to put a -6 in here, a -6 in here, and a -6 in here. And that is also going to give me the point -1/2. So if you need to take a minute and just verify my numbers, go ahead and pause your video. So as we look at this, and I went ahead and counted, just figured out another point on side of this vertical asymptote. So we know it's trapped here, so it's either going to wiggle down, wiggle up, be a U pointing up, be a U pointing down. And so I just kind of need to know what's going on each side of my asymptote. So at -4, it's +1/4, so it's up here. At -1, it's down here at -1/2. So that means that this middle part of my graph is kind of doing something like that. And then on this side, I went ahead and calculated one more point, so I know I have 1 2/3. So this is probably going to look something like this. And then this side over here is -6 1/2, so I'm down here, and so this graph is going to kind of do this. So that way I can kind of look at what's going on the graph. But really, to be able to find the domain, all I need to do is leave out the holes and the vertical asymptotes, or the x value of the hole. So if I start over here in -infinity, then I'm going to go to the -5, which is where the vertical asymptote is. And then I'm going to skip the vertical asymptote and move over to 0. And so that is the next vertical asymptote. And then I'm going to move over to from 0 to 4. And then I'm going to go from 4 to infinity. So that's what the domain is going to look like when you skip the features. And we just kind of did F and G together at the same time. You should be able to punch this into your calculator and kind of see the same kind of representation on your calculator screen that we see on the paper. So it was just a way to practice a little bit about making sure we understood all of these characteristics that we've been finding, how they're going to affect the graph, and then being able to kind of verify or know if we're right or not. All right, so I have my little calculator here, but actually that's kind of pertaining to G right there. So I just wanted to kind of make sure you realize that that went down to the next part of this. All right, so the next thing we're going to do is example 3. The graph of the rational function is shown. Write an equation in factored form for f of x. So what are the characteristics that we can see? We can see we have a hole. If you look real careful, it's right down here. So we have a hole at x equals 4. So remember, that's the common factor. And then we have a vertical asymptote at x equals 2, and that's in the denominator. And then we have a horizontal asymptote, so it's right here. You're having trouble seeing it on your paper. And the vertical asymptote was at 2 right here. Sometimes the graphs don't always print the best. So we have a denominator. So we have a horizontal asymptote at the same factor, right? So we would be canceling something out. So we're going to have a horizontal asymptote at y equals -1. So that might be something like negative x squared over x squared or something along that lines. And we know we have a 0 because it crosses the x-axis right here at x equals 3. And that's going to affect the numerator. And this at the ratio. All right, so I have to put all of these characteristics into my equation. So paying attention to what it tells me to name my function, which is f of x. So I'm going to say f of x equals, and then I have a ratio of -1. So I'm going to put my negative out here in front so I don't forget about that -1. And then I know I have to have a common factor canceling out at 4. So I'm going to have x minus 4 in the top and bottom because that has to cancel out to create that hole. And then I have a numerator, or I need to go in the numerator for my 0. So that's going to be x minus 3. And then I have a denominator of VA in the denominator. So that is going to be at x minus 2. So would this cancel and give me a hot -1? The powers on top are x squared, powers on bottom over x squared, and this negative in front means that I'm going to have that negative answer. So this is one possible solution or one possible equation that we could have for f of x. So go ahead and pause your video and see what you can do with example 4. But let me make sure you can see where all the asymptotes and stuff are. So there's an asymptote there. On this one, there is a hole right here at 2. What else? There is a 0 happening right here at 1. And what about vertical asymptotes? So it looks like we have a vertical asymptote here and another one right here at 0. So there's all the characteristics that you need to know to be able to write your equation. So write an equation for the function g of x. So you're going to say g of x equals and come up with your equation. So pause your video now. Okay, so let's see how you did. So I noticed that my other functions on the rational odd would have a branch here and a branch here, and I noticed this one went the other way. So I know that there's a transformation that happened. So I'm going to put my holes where they cancel, which is right here. but my vertical asymptotes in the bottom, which are here and here. And remember that each vertical asymptote represents a bunch of points on that vertical plane. So make sure that you state each equation for each vertical plane separately. And then we're going to have a horizontal asymptote at 0, so the degree on bottom has to be bigger than the top, which it is. And then we have a 0 at 1, so I needed a factor in the top at x minus 1. All right, so moving on, recalling that a rational function, if the degree of the numerator is 1 greater than the degree of the denominator. So remember, this is case 3 where the numerator is dominating the denominator. And more specifically, when that happens and the degree on top is 1 more than the degree on bottom. So the numerator degree is degree on the bottom from the denominator plus 1. Then we're going to have a slant asymptote. And so we talked about in lesson 1.7 that we could use parallel lines to the slant asymptote to be able to determine the end behavior. But today we're going to actually work on finding the equation of the slant asymptote, so the actual equation. So if you recall from last time when we looked at this, we looked at a graph, and then we looked at the actual, and we looked at the parallel. So let's look at that graph for a minute. So last time, or I guess this is in lesson 1.7.1.8, we looked at just a rational function. And so this was the rational function. And then we said we could use the ratios to create a line parallel so we could describe the end behavior. And then we talked about, well, how does that look compared to the actual one? So this is the parallel line that lets us describe the end behavior, and this is the actual slant asymptote. So you can see it fits closer to the actual slant asymptote, but because these are parallel lines on each end, they're doing the same thing. Well, today we're going to focus on actually finding that exact asymptote. Okay, so this is what we're going to work on finding, this slant asymptote that falls in the equation, or for the actual equation. So just reviewing, and when I say old method here, I just mean this is the numerical version you learned in elementary, and this is what it's going to look like when we start putting the letters in that you learned about in Algebra 2. So for instance, if this is my problem, the front number is going to go inside the division box, and the number you're dividing by is going to be outside, and then you would do the division. So you would say 21 goes into 67, 3 times 21 is going to give me 63, and when I subtract this row right here, then that's going to be a difference of 4, and I bring down the next digit. Then I say what times 21 goes into 46, and that's 2. Then I say 21 times 2, which is going to give me 42, and I subtract and find my remainder to be 4. So if we're looking at all of the parts here, this is the quotient, this is the dividend, this is the divisor, and this is the remainder. So when we're writing this back into our rule, then we would say the quotient plus the remainder over the divisor should equal this dividend of 672. So then the quotient of my problem here is 32, the remainder is 4, and the answer then would be 32 plus, or just the fractional part, because a mixed number is the whole number part plus the fractional part, and that would be 4 over 21. So that's the basic gist of what you learned in middle school and elementary school. So now we're going to look at polynomial division. So this is numerical long division, and this is polynomial long division, okay? So the process is the same for most of it. You just have to pay attention to a couple things that are different. So the first number is still going to go inside the division box, so that's going to be 6x squared plus 7x plus 6, and then we're going to have our division, and then we're going to divide by 2x plus 1. So to do this division, remember that it's what times 2x gives me 6x squared. So that's going to be 3x. So 3x times 2x. But you have to multiply when you do the multiply step by the entire divisor. Okay? So 3x times 2 is going to give me 6x squared. 3x times 1 is going to give me plus 3x. And we're going to line everything up in columns based on our variables. And then over here we would subtract. Well, we're going to subtract here too, but we're subtracting the whole line. So that's going to affect the sign on each term. And if I did my math right, then these leading terms should eliminate. And then I'm left with a positive 7 and a negative 3, which is going to give me a positive 4x. And I bring down the next number. So then I do it again. So I would say, what times, let's see, change colors here. What times 2x gives me 4x? And that's going to give me 2. And then I'm going to do 2 times 2x, which is going to give me 4x. And 2 times 1, which is going to give me 2. And then when I subtract that row, I have to change all the signs. So let me do that with a color. So you can see that a little bit better. So we'll do a negative here, and we'll change the sign here. And again, if I did it right, these eliminate. And then I have 6 and a negative 2, which is a remainder of 4. So if I'm filling out my pieces here, then the quotient is what's on top. That's the 3x plus 2. The remainder is what's down here on bottom, which is 4. And then the answer is the quotient, and we'll put parentheses around it because it's a list of terms, plus the remainder, which is 4, over the divisor, which is 2x plus 1. So that's what long division with letters looks like. Okay, moving on to example 5. So as we move on to example 5, we're going to use long division to find an equation for the slant asymptote. And the slant asymptote is actually just going to be the quotient. Because if we go back to our special cases that we looked at last time, and let's say this is the case where the bottom is growing faster than the top, when I start increasing numbers here, I get this fractional value in the bottom that gets bigger, which makes the value of the fraction get smaller and approach 0. So the remainder will go eventually to 0, and it won't affect anything here. So if nothing else, remember that it's the quotient that creates the equation of the slant asymptote. And remember, slant asymptotes are lines, so that's why it wouldn't make sense to have this as the equation of a line. All right, so pause your video, and I want you to do the division here and get your division for h of x. So pause your video. Okay, so once we've done our division, then the equation of the slant asymptote is going to be y equals just the quotient 3x minus 1. So that's how you're going to get your slant asymptotes, by doing the division. All right, so equation 6. So I want you to find the factored form, find the vertical asymptote, find the horizontal asymptote, and find the slant asymptote. Remember that you're never going to have a horizontal asymptote and a slant asymptote, so make sure you know if it's the case where you're going to have a slant asymptote, which would be the special case where the numerator is 1 more degree than the denominator, and the top is dominating. All right, pause your video, work through example 6. All right, how did you do? So we factored and canceled and got our simplified version, which is also the same thing as x squared minus 2x, remember? So the x's that I have left here and here, which are right here, are my zeros. This is the vertical asymptote, and where they canceled would be a hole. So there's going to be a vertical asymptote here at the 0 of this factor, which is x equals negative 1. Don't forget to write your equations. There is not going to be a horizontal asymptote because the numerator is going to dominate the denominator. And in this case, it is a n equals d plus 1 because it's a power of 2 on top and a power of 1. So that means we're looking for a slant asymptote, and we do the division. So I did the division with this piece, which is the same thing as x squared minus 2x over x plus 1. So this is the factored form. This is the unfactored form. So the top goes inside, the bottom goes outside. Made sure when I was doing the multiply through that they canceled out. I had a remainder of 3. Remember that the remainder is not going to affect the slant asymptote. The quotient is x minus 3, and so that's how I write the equation of the slant asymptote. All right, let's practice example 8. So you have a function already in factored form for you. So I want you to do A, finding the horizontal asymptote, or sorry, not finding, you're trying to decide what's what. So do whatever calculations you might need, and then pick which is the correct answer. Have supporting work anytime you do a multiple choice question. So pause your video. Okay, so as we narrow down our choices, we're looking at what it's asking. And so because we at x equals -1, because I had to factor the bottom, but notice it cancels at x equals -1. And that just means there's something going on there, but it's actually got a vertical asymptote here, so there are no holes. So then when this one says 1 hole, I should be able to eliminate that. This one should be my answer choice because that vertical asymptote is what's left in the bottom, and that's what we're looking at. Okay, so my bells are ringing, but we're almost finished here. So let's go ahead and pause our video and see if you can sketch a picture of this rational function with the following properties. So you're going to have to interpret what the properties mean and then do a rough sketch of what that might look like. So pause your video one last time and finish this last problem. Okay, so this is one possible solution. So when I was looking down here, I looked at the -1 and I have infinity going in one direction and a -1 and the infinity going in the same direction. But when I look at going to infinity, I have this one going to negative infinity and this one going to positive infinity. So because of the behavior here at my vertical asymptote and the behavior of the function going to my infinities, then I knew it had to be going up this way and I had to be going down this way. But remember, as we're approaching the vertical asymptote, they're both going down. So what that told me is I probably had some sort of slant asymptote, because if this is going to negative and now it's coming back to negative, it has to have that curve. And if this is going to negative infinity, but back this way, it's going to positive infinity, it kind of has to fit in there, something like that. So this is by no means the only way you could have sketched that, but it kind of gives you an idea a little bit about what's going on and how that slant asymptote might guide the graph when you're looking at those end behaviors. So go ahead and take care of your daily practice and make sure you can handle all of the rational function stuff. So what have we talked about in all of our lessons? We've talked about what a rational function is. We've talked about zeros. We've talked about vertical asymptotes. We've talked about holes. We've talked about slant asymptotes. We've used end behavior to describe things with our graphs. We've wrote equations. We have graphed equations. And we have used long division to be able to determine slant asymptotes. We've also used the ratio of those leading terms to create a parallel line so that we can describe end behavior, and we've looked at all the cases of end behavior. So this is a really good wrap-up of all the graph characteristics, behavior characteristics, and some of the mechanical things that we need to be able to do when it comes to rational functions. Thanks, guys. See you next time.